Hey everyone, welcome back to discussion 8. We're going to continue talking about Newton's laws of motion. So let's jump right in. Textbook page 149, problem 41. So two blocks are connected by a rope that passes over a massless and frictionless pulley as shown in the figure. Given the values of the blocks, determine the magnitudes of the tension in the rope and the block's acceleration. So we need to find the magnitudes of the tension, and we need to find the acceleration. Okay, so finding the overall acceleration is going to be the easier thing to do, and we're going to start with that. So I'll draw a diagram, and I'm gonna write out the given information from the problem. Okay, so the first thing that we're going to do is we're going to sum up all of the forces. Okay, so I've drawn a force diagram here. Let's make it a little larger so you can see. That's pretty good. Move these over here. So I've written down the givens as well. As you can see, we're told these two informations in the problem. And then we're asked to find these four things. Okay, so we have a tension force right here. Right, that's tension 1 pointing in the positive y-hat direction, and we have a weight force pointing in the negative y-hat direction. This is the weight force 1, so I've identified them. This side, this is block 1, so we have Ft1 and Fw1. This is M2, so we have Ft2 and Fw2. Again, this is pointing upwards. This is your tension force, and this is going to be your weight force for number 2. So let's sum up everything. Recall that the sum of forces on a system is going to be equal to the net mass times the net acceleration. Okay, so let's sum up the forces. So what do we have? We're going to have Ft2 plus Ft1 plus Fw2 plus Fw1. Okay, and so we really need to make a clear indication of the axes here, and recall that I had actually said that just said that this is positive y direction and this is negative y direction. Well, that's true, but if we expand this thing, so this whole thing is a system. All of this is one system, right? And we actually have this one rope. This can be considered one-dimensional if we unfold it. So what I mean is this. Okay, so I have just taken the time to draw this diagram here. I've unfolded, right? So I've taken all of this stuff. I guess I didn't draw I could draw the boxes here, but you get the idea. So the tension force here, Ft1, is pointing in the opposite direction of Ft2 here. Same thing with the weight forces. This one's pointing this direction, and this one is pointing this direction. So we can define a convention such that we have a one-dimensional axis, and that these are opposites instead of saying that they're in the same direction as before. So let's write this out. So then we have Ft1 minus Ft2. Those are going in opposite directions, right? Minus Fw1 plus Fw2. Recall that those are also going in opposite directions. Okay? So now we have Ft1 minus Ft2 minus M1 times G, right? Because that's going in the negative direction, plus M2 times G. Okay? Next, we simplify a little bit. We say this acceleration is going to be AT1, I guess, minus M2 AT2. Okay, plus G, and then we can sort of simplify here. We've got M2 minus M1. Okay, At this point, we need to recognize that. Sorry, this is m1, m2. Okay, so m1 times the acceleration in the tension force is going to be equal to m2 times the acceleration of the tension force the other way, because if it's not, then this rope would break. Okay, so these forces are actually in equilibrium here. These two are. Okay, so those are going to cancel. That is the main point here. So then we're left with the sum of the forces is equal to G. Oops. Yeah, so it's equal to G times M2 minus M1. Okay, and recall that this is going to be equal to the total mass times the total acceleration. Okay. One good thing is we actually know the values of the mass, so we can actually talk about what that value is going to be. So here, let's just do this. We're going to have G m2 minus m1 over, right, I'm just taking this to the other side here, okay? So this is m net, which is going to be m2 plus m1. So we are well on our way to knowing what is the overall acceleration of the system. Okay, so let's just plug in some values. We got 7 meters per second squared, or about negative 2.04 meters per second squared. Okay, that's the overall acceleration. Now let's note that this has come out negative, so we just want to check to make sure that this is going in the right direction. So this is a negative 2.04 meters per second squared. So we go up to our diagram, we know that these two things are going to cancel out. We know that m1 is heavier than m2 by comparing the weight forces. We're given the values, right? So m1 is higher value than m2, so this is going to go downwards. So this is going to go this way. So how did we define this? So here's our weight force, Fw1, and we defined it such that that was in the negative direction. We're given a negative acceleration, so that actually matches up. So that works. Okay, now we want to find the tension force. Okay, so recall from earlier that we have an equivalence, right, of Ft1 and Ft2, and these are going to equal M AT1 equals M2 AT2, right? And so we actually want to find both tensile forces. We're saying that they're equal, but let's find out if they actually are, and if they are, that means we did something right. Okay, so we want to find, let's just start with Ft1. So let's say that m1 times the overall acceleration on m1, which we found earlier, is going to equal m1 times the tension force minus m1 times. So we want to know what is AT1. Well, m1's cancel in this equation. We're given that an plus g is equal to AT1. So that means that AT1 is equal to 9.81 minus 2.03. Okay, by how we've defined this. So that is going to give you m1 times g minus 2.03 is equal to Ft1. Okay, so that's how I got to this point up here. Okay, so I'm going to just get rid of this. And then we're going to go, we can plug the values in here. So this gives us, what is this, 15.93 times 9.81 minus 2.03. That gives us a value of 123.93. Okay, this is going to be newtons because this is Ft1. Okay, so then we can solve for Ft2 using the same method. This is negative and this is positive. taking a quick look at this, ft2 is equal to m2 at2, that's the acceleration of the tension force, is going to equal the overall acceleration on m2, negative m2 times at2 plus m2 times g. Well, the m2's cancel. We're left with a net acceleration is equal to negative at2 plus g. So we just take this over here and this over here. That gives us at2 equals g minus an, which is going to be 9.81 minus negative 2.03 equals 9.81 plus 2.03. So that means that ft2 is going to equal m2 times 9.81 plus 2.03 meters per second squared. Okay? Okay, that actually gives us a value of 123.83. What was our other one? 123.93. Oh yeah, and I actually made a small error here. This should be 2.04. So because of the way I rounded it, these are slightly different, but they're close enough to where I'm going to say they're equal. Let me just double check before we move on. I entered the value that we had originally found, which is, where was it here? Negative 2.037 meters per second squared. Then I end up getting values of 123.801 and 123.823. So again, there's a little bit of rounding discrepancy, but I mean, these are the same. So we can say that ft1 is equal to ft2 is equal to 123.8. Say approximately equal to 123.8 newtons. So that's your answer. Okay, so problem 46. A heavy crate of mass 50 kilograms is pulled at constant speed by a dock worker who pulls with a 345 Newton force at an angle theta with the horizontal. The magnitude of the friction force between the crate and the pavement is 212 newtons. So draw a free body diagram of the forces acting on the crate. Okay, let's do that first. Let's go down here. This is number 46. So we have a floor here. We're going to have some sort of crate. That there. Let's give it a different color. We want to be able to see it, right? Then we have a force that's pulling it here, and it's making an angle theta with the horizontal, right? Okay, so now we need to look at the forces. So the forces are, well, we have a weight force going downwards, right? This is going to be, we'll call this Fw for weight force, which is always equal to mg. Okay, and then we have here, this is going to be the normal force coming off of the normal force, which is the ground pushing up on the box, right? The ground pushing up on the crate, that's your normal force. Since we're told that this thing is pulled at a constant speed, and that there's some friction, we can assume that this thing is not jumping off of the ground, okay? This is not jumping up this way, it's not breaking through the ground, so that means that the weight force has to equal the normal force, okay? That will be useful later. Okay. We also have our applied force in this direction. We can call this vector here, this is our applied force. Okay? We're going to have some components for our applied force. This would be Fay, this would be Fax. Okay? And then we have a frictional force that is resisting the motion in this direction. So we'll call this F of mu. Now that we know we have a frictional force, this we're going to have to look at this in a little more detail. So before we go ahead and jump to conclusions, let's actually write everything out, because we're going to need to sum the forces. Okay? Well, so if we look at everything that's going in the y direction, again, this is not moving in the y direction. It's not jumping up here due to the normal force. It's not breaking through the ground due to the weight force. It's not jumping off of the ground due to the applied force. So that means that we have F sub n plus Fay, the y component of the applied force, plus Fw. This is all going to be equal to 0. So that tells us that our resultant vector y component is equal to 0. Okay, so we're after the angle here. I think that's the next thing we're asked, right? What is the angle of the rope with the horizontal? So we can find that. Let's recall that our resultant vector is going to be rx plus ry. So we have x and y components of our resultant vector. But again, it's not jumping up or breaking through the ground, so r sub y is equal to 0. Okay, so now what we need to look at, what do we have in the x direction? We have a resistive frictional force, and we have an applied force component in the x direction. Okay, so let's write those down. We're going to have F sub mu plus F sub ax. Okay, we are told, so this is going to be here, r sub x. We are told that this thing is moving with a constant speed. So what that tells us is that the overall force, the overall resultant force on this thing is equal to 0, because what we're saying is the mass of the crate times the acceleration, right? This is equal to 0. There is no acceleration. It's a constant speed. So let's put everything together. So here we have r sub x plus r sub y. That's going to go away. That equals 0. This actually equals 0 as well. So now we're just left with 0 equals F mu plus F ax. Okay, so now at this point, we can start looking at the values that we have. We're told that the frictional force is 212 newtons, and it's moving in the negative x hat direction, right? It's moving this way. That's the frictional force. The applied force moves in the opposite direction, so these are going to be opposite signs. So 212 newtons, right? This is negative. Plus, we're told that the crate is 345. Sorry, no, that's not right. We're told that the overall magnitude of the force is 345 newtons. And we're given an angle theta, and we're only talking about the x direction right now. So it's cosine theta. This equals 0. So then, pretty much now we have one equation, one unknown, and we can solve for theta. So let's do that. Okay, a little bit of quick algebra there. And then this is going to give us 52.08 degrees with respect to the horizontal. So now let's see what else we are being asked, right? This was problem 46. What is the magnitude of the normal force exerted by the pavement on the crate? Okay, so since we want the normal force, which is in the y direction, we can use the equation we had earlier, which is where we sum up all of the y direction forces to 0, because we did that a minute ago, and then we can solve. So let's set this up. I'll just copy this down here. Make it quick. There we go. We're looking for the magnitude of the normal force. So let's just take these two things to the other side. Minus the weight force right, minus the applied force. Okay, so we are told that the mass of the crate is, what, is 50 kilograms, right? And then we multiply that times g, because this is the weight force. Okay, next we have a negative. We know that the y component here for the applied force is going to be positive because he's pulling up this way. So when we took it to the other side, it remains negative. And we have 345 newtons times sine of our angle, which is 52.08 degrees. Right, and then we solve for it. And this is all in the j-hat direction, but since we're talking about only the j-hat direction, we really don't need to worry about this. We're just looking for the magnitude. So let's do this math. So plugging all this in, we get about 218.34 newtons. Is our normal force. Okay, let's see what else we got. Problem 79. Okay, so now we have two blocks on a pulley on a ramp. One of them is off the ramp. Two boxes with masses 4 kilograms and 10 kilograms are attached by a massless cord passing over a frictionless pulley, as shown in the figure. The incline is frictionless and the theta is 30 degrees. Draw a free body diagram for each of the boxes. So, okay, we really want to look at which forces are acting on the crate or the box. Both boxes, right? So we have two boxes, one here on the ramp, one here hanging on the pulley. So we're going to have this ramp is going to be pushing straight up against the box. This is going to be our normal force. We're going to have a weight force that's pulling downwards, right? It's also going to, when I'll show you in a second with some trig that it's also equivalent to pulling parallel down the box. So that's actually pretty useful. On this one, we have a tension force. Oh, also there's a tension force here going in this direction. There's a tension force here going in this direction. And there's a weight force coming down. Okay, so I started to draw these. See if we need these. Look at the forces on each individual box a little closer. So again, we have the weight force coming down, tension force going up, normal force. Okay, those are the three on the box on the ramp. And now, so how did we get the weight force coming here as opposed to here? Well, this could still be your weight force, so mg sine theta. But we can look at this. If we draw a triangle here, right, this is going to give us an angle beta. So we have theta and beta. This is going to be perpendicular, right, to the box itself and to the ramp. And so this gives us 90 degrees. So here we have theta again, right? Because beta plus theta is 90. Because this is 90. Okay, this is a right triangle. So now, given this angle, sine theta is going to give you this parallel vector here. Okay, so that works out for us. All right, and then the next one again is just up, and we have a tension force up and a weight force down. Okay, I think that's probably good. So that's what you want your free body diagram to look like. So we have three forces acting on the box on the ramp and two acting on the one hanging off the pulley. We're asked to find the magnitude of the acceleration of the boxes. So the overall acceleration of the system, essentially. Okay, so then we just want to sum up all of our forces, right? So we have Fw2. Recall here from our diagram that we've defined this as M2 on the ramp, M1 hanging. Okay, so we have Fw2 plus the normal force, right, plus the tensile force, and then we have a tensile force for box 1, and we have a weight force for box 1. Okay, this is going to equal total. This is going to equal total times the acceleration, net acceleration. Okay, so we need to define which direction these things are going. So let's say that this is going to be in the negative direction. Okay, this is positive. So this is negative, this is positive. This is positive, this is negative. Okay, if this is negative and this is positive, that means this is negative and this is positive. Remember from before, we unfolded our system, right? This is still essentially, you can count this as like a one-dimensional problem. We're simply, we're using Newton's laws to sum up the forces. That's what I mean to say. Okay, so then we just said that this is going to be negative. This is m2g sine theta, right? We're also going to have normal force plus tension force, and then a tension force again, which it's going to be negative. And then we have positive m1g equals m total a net, right? Okay, so let's recall also from earlier when we had our pulley problem that we had tension forces were equal, because otherwise, let's see if I have this, otherwise this rope would break, right? So these are going to cancel each other out, which is good. We want that to happen. We're trying to simplify this problem, so those go away. All right. Okay, so we still have this Fn2, and we need to figure out where's that going to go. So, oh, I already wrote it down here. So what we're looking for is, well, if gravity is pulling down in this direction, here, straight down from the block, right? We already figured out that this is theta here. So this parallel direction force is going to be, so this is the weight force pulling down. This parallel force is going to be here, right? So we're saying this is m2g sine theta. We also have this component on the other side, which is going to be m2g cosine theta. We're looking at components. That's really what we're doing. So we're breaking this weight force down into components. We have this component and we have this component. This component cancels with this component, or this force, right? This component of the weight force and this normal force are going to cancel. So what we want is we have F, we'll call this FW2, we'll say that's just X and Y. So these cancel as well. So that means that this goes away, and we're just left with this here. So this is going to be what we are left with. Okay? So we have M1 plus M2. A net is equal to negative M2g sine theta plus M1g. All right? That means that the net acceleration is going to be g times m1 minus m2 sine theta all over m1 plus m2. That's your answer. Okay, again, just to be clear about how to find your forces, because I remember having a little bit of trouble with this when I was going through undergrad. Let's just look at this one more time briefly. Okay, so here we have a ramp. Here is a box. Here's a box. There we go. If we can get this box onto the ramp, that would be ideal. There we go, something like that. Okay, so we know that the ramp itself is actually pushing up with a normal force onto the box. That's our normal force. Okay, we also know that that gravity is actually pulling this thing downwards in this direction. Okay, well, if we set something up where we have a perpendicular line that's opposite the normal force, so it's perpendicular to the ramp, well then this is going to be beta, and this is going to be back to theta, right? So now we have two components for this gravitational force pulling downwards. We have a component going this direction. Okay, so now we have a force going this direction, and we have a force going this direction, right? And so these are both components of the force itself. So we have, this is going to be the weight force of the box sine theta, right? This is the weight force of the box cosine theta. Now this cancels with this, okay? So those go away in summing your forces. Also, if you have a frictional force, it's going to be going this way. If you have a tensile force, it's going to also be going this way, provided that the ramp itself is inclined enough to pull this direction. So here we have our mg sine theta, right? Because this is parallel. This is parallel to this, so here and here are the same, right? So that's the easiest way that I can think to explain it, and I think that's going to be useful in doing these problems for you. All right, so moving on, the next thing we're asked to find, we found the magnitude of the acceleration of the boxes analytically, but we did not plug it in numerically. So we can plug in all of the values here. So I'm just going to do that. Okay, because of the fact that we defined this as being negative, this direction, right? I plug in values, and what I get is 9.81. This was 4 kilograms minus 10 times sine 30. Okay, and this is going to be 14. This gives us a value of approximately negative 0.701 meters per second squared. That's our answer. That's the magnitude. Now we need to find the next part, which is going to be, what is the tension in the cord connecting the boxes? This is going to be M1, right? And then we had a tension force up here, FT1, and we had a weight force down here, which is FW1, I'm going to say. So let's just use that information. And recall that we just found the net acceleration. So net acceleration on M1 is equal to, since this is downward, this must be upward. This is upward, this is downward, right? So what I'm saying is that this is negative, this is positive, this is negative, this is positive, okay? So that gives us M1G minus M1AT1, right? We're trying to find the tension force overall, so we need the acceleration in that vein, right? So we have A net, let's do it this way. AT1 is equal to G minus A net, okay? Which is equal to, we just found that this is going to be negative 0.701, right? Meters per second squared. So let's do this. Let's say, since it's asking us to find the tension connecting the boxes, we're going to say, recall that these are going to be equal, right? So we're also saying that we're going to have 4 kilograms times 9.81 plus 0.701. That gives us a value of approximately 42.04 newtons. That's the tensile force. That's the answer. You can also do it the same way that we did it for block 1. You can do it the same way for block 2. You just have to make sure that you sum up all of your forces correctly, okay? Next, we are asked to find the speed of the boxes when time is equal to 3 seconds. What is the speed of each of the boxes 3 seconds after their system is released from rest? So let's recall that we have kinematic equations. Remember I was saying that we're essentially moving in one dimension. From the last, it was like 1 or 2 problems ago where we had a pulley problem, and I expanded the pulley, and then we could see that we're really just moving in one dimension along a rope, right? So let's see, we have a constant, we can say we have a constant acceleration. We have v naught plus acceleration times time. Okay, we're going to say that v naught is equal to 0. So then v is equal to negative 0.701 times 3 seconds. Okay, so after 3 seconds, what does that give us? That gives us, let's just plug it into the calculator, negative 0.701 times 9 times 3. Oh, negative 2.103 meters per second. Because this was in meters per second squared times seconds gives you meters per second. So it's negative because recall that we're sliding down the ramp. I defined this direction earlier, I defined this direction to be negative. So it's going to be sliding down the ramp. If it's big enough, after 3 seconds, it'll continue sliding down the ramp, and it's going to be going at this velocity or at this speed. Say at this speed. Because I think we were asked to find the speed, right? Yep, what is the speed? And there you go. Number 49 is essentially the same problem that we've just done. So I'm going to set it up. I'll go through it. I'm going to set it up real quick, and then I'm going to solve it. But I'm not going to take the time to really explain what I'm doing because I pretty much did it. It's going to be exactly the same as what I did before. Okay, so we're given a block. Right? This is 20 degrees. Sorry, it's a ramp, of course. This is M1. This is M2. Okay. Now we're given values for M1 and M2. M1 is, here I'm just going to do this. Okay, we're given no initial motion. It's released from rest, which is what we would expect. Do this again real quick. So here we have, this is theta. This is going to be mg cosine theta, m2 cosine theta, and this is going to be m2 g sine theta, right? So this is m2 g sine theta, recall. This is your tensile force. This is your normal force. And remember from last time, this thing and this thing cancel. Also, let's call this here tension force, and the tension force are also going to cancel. So that leaves us with M1, which our weight force is M1G. Okay, so that's a really quick, sloppy version of what I had done earlier. Okay, so we need to find the net acceleration. Okay, so I canceled the normal force with this component, the cosine component of the force. We're left with a sine component. The tensile forces are going to cancel, so we're left with only the weight force and this component here. This is all going to equal the net mass times the net acceleration. Right, so I've written it all down. That means A net is equal to 1 over m1 plus m2. Let's put g here, g m1 minus m2 sine theta. Okay, so I plugged everything in, everything that we know. M1 is, I wrote it down, 7, and M2 is 2 kilograms, theta is 20. So I plugged everything into this equation here. And I got the acceleration is 6.884 meters per second squared. Okay. So that one went rather quick, as expected, because we just did another problem that was pretty much the same. Now we need to do it again, because problem 50 is essentially the same problem, but we're given some kinetic friction. So same masses. We're given a net acceleration. They want us to find the magnitude of the kinetic frictional force between the block 2 and the ledge. I should comment real quick that the acceleration we found, I forgot to mention this, is positive, and that is because we are going in, because M1, which is 7 kilograms, is in fact heavier than M2, which is 2 kilograms, so we're actually going to be going this way. Remember, I defined this direction, going this way, as negative, and this way as positive. We ended up with a positive acceleration overall, and that makes sense, again, because this is heavier. So let's set up our problem to find the magnitude of the frictional force. The reason I pointed that out is because since we're traveling up the ramp, the frictional force is going to be down the ramp. M1, here, just drawing another quick diagram. So since we're going this way, remember our normal force, well, let's actually, before we jump to conclusions, let's put this here. Normal force, Fn2, right? Here we have our, it's going to be m2g cosine theta. This is going to be m2g sine theta, negative. Okay, right, because we have our weight force pulling downwards. Okay, if you're confused about this, then see the, I think it was problem 2 or 3 from this lecture. Okay, so now we also, so we have this force coming this way, and we also have another force, the frictional force, giving us some drag as we're going down. So we have two forces kind of pulling in the same direction. We have the component, the sine component of the weight force for M2, and then we also have the frictional drag. Because remember, we're going this direction, so the frictional force is going to be pulling this direction, this way. Okay? So let's sum up our forces to see where we're at. Okay, we have, I'll come up here. M net, acceleration net, is equal to negative frictional force, negative weight force. Actually, what we'll use is, we want to be doing this, for just the second block, okay? So now we have a negative frictional drag force, we have a negative weight force because it's pulling down the ramp, so that's going to be FW2, and then we have plus the tension force. Okay, we're looking for the magnitude of this force. So, well, we actually do have a value for the net acceleration. We're given in this problem, it's 0.134 meters per second squared. So it's quite a bit less than our 6.884 meters per second squared. And that makes sense because now we have a frictional force pulling the other way. So let's figure out what we got. Let's just do it this way. Equals negative m2. What do we have? It was 0.134 minus m2g sine, what was our angle? 20 degrees. Plus our frictional, or our tension force for the second block. So this tension force and this tension force are going to be equivalent. So to find this one, I have to go through and deal with all of these forces. But for this one, I don't have a frictional force. I only have tension and weight force. So let's just use that again. Okay, so I just went ahead and solved for this real quick. So recall from earlier, again, I'm not going to spend a lot of time on this, but I set up the net acceleration times the block. M1 is going to be m1g minus m1 tensile acceleration, right? Then we can solve for the tension acceleration, gives us this. So the tension force for the first block is this here, okay? So, again, let's do it this way. Here is a This is kind of an extra aside calculation. I'm only showing this again just in case there's any confusion where I'm getting the tension force. So we also have Ft1 is equal to Ft2 is going to equal M1 AT1. Sorry, this is M1, which is equal to M1 times g minus the net acceleration, which is equal to M1 9.81 plus 0.134. So what all of this means is I can just take this equation here and plug it in. Plug in everything that we know. So this is going to be just trying to go quickly so that I don't run out of time, because I don't want to take too much of your day. I know you have lots of homework. 3, 4. Okay, so here we go. This is minus. Okay. Okay, so I just plugged it all in on my Wolfram calculator, and I'm getting that the frictional force, the magnitude of the frictional force, is going to be 60.7536 newtons, or approximately, we'll just say 61 newtons. I did quite a bit of rounding there. I'm just, obviously, depending on what sig figs you want to use, you would have to kind of determine that. So recall that at this point you should have seen we have a kinetic frictional force is equal to a frictional coefficient times your normal force. And from our diagram earlier, we have shown, let's find the good one here, we have shown that the normal force is equal to this mg cosine theta component. Okay, so now we have some coefficient times m2g cosine, it's going to be 20 degrees. Also, we just found this, right? This is equal to f of mu. So f of mu equals 60.7536. So we set this up. 60.7536 is equal to mu 2 kilograms times 9.81 times cosine of 20. Okay, so then we solve for it and we end up with, let's just take all of this. We take this. And then we end up with a value of 3.29. This is scalar value, right? Because this was a force. This was in this was in newtons. We have kilograms, meters per second squared. This is kilograms, meters per second squared, right? So these units cancel, and we are left with a unitless scalar value, which is your kinetic friction coefficient. Now, 3.29 seems pretty high, but that's what we're getting. If you took the inverse of that, I think it would be like the inverse of this 1 over mu is about 0.3, which is what I would have actually expected. But let's say, look at this real quick before we go. Our acceleration was originally 6.8, so almost 7 meters per second squared, and we went down a lot to what we're given. It's 0.134 meters per second squared. So that's a huge drop, okay? So we went from 6.8 to about 0.13, right? So I'm going to say it's okay that our value is really high. That's what we would expect when seeing that sort of change. All right, till next time.